So guys, this is one of the most widely used library, that is Scikit-learn, short form is Sklearn, for building the machine learning models with Python. Okay, so they have their own website, that is scikit-learn.org. Can you see that scikit-learn.org/stable? Stable as in this particular module, the package that we have, it's the most stable package. And virtually, like if you think of any kind of a machine learning model, the commonly used model, all are available in this. But when we talk about building up the machine learning model, so there are 4 or 5 things that we have to remember. And they have mentioned everything on their front pages over here. If you see, this is Scikit-learn enabling the machine learning in Python. Everyone whosoever is working on Python, trying to build ML model, no matter in which part of the world they exist, okay, they are using this library. They are taking the usage of this library for any application. So you see this, yesterday we were talking about this classification only. So that one is classification, then second one is regression. With the help of regression, we are able to achieve the forecasting. So here we try to predict the relationship between the two variables, like one become dependent and one become independent variable. That's regression. And for the unsupervised learning, where we don't have the labels, we have the clustering for them, right? So these are the 3 different aspects of the machine learning algorithm. But to achieve better performances from these 3 things, we have this dimensionality reduction. So we'll be talking about that also, dimensionality reduction. This is model selection, wherein you will get so many functions to do a little bit pre-processing on your data in terms of splitting up the data, doing the cross-validation of the data. So whatever term that I was using yesterday, we will be using the function of model selection to achieve that. Okay. And then we have pre-processing. Now, pre-processing is something wherein, like, when we are digging deep into the increasing the performance of the machine learning models, then we use this. Like, instead of processing your data directly, we first made it through pass with certain function that is known as feature extraction. So how we change our features in such a way that it becomes more better representable with respect to that class, so that my classifier will understand it in a more better way, right? So when it understands in a more better way, it will start giving me the results in a more improvised way. For example, if I'm getting only 83% accuracy, now how I can move from 83 to 89? For that purpose, you have to utilize this either dimensionality reduction plus this pre-processing. So that's why this is, it's very, very important. That's it. So that's it. These are the 6 things. When we say I know machine learning, so at least these 6 things you should know. This is open source community. This is being made just for everyone who can utilize the concept of machine learning to build any application or innovate in application. So we are also going to use this. Okay. So now let me just show you. Let me open up the Jupyter notebook. Let's try and understand with one simple data. And that data, I'll show you the description also. So what are the supporting libraries of the Sklearn, which enables you to start implementing ML model within your Python environment are, see this. Now in your NumPy and Pandas, I'm considering that you have at least a entry level understanding that yes, this is how we import the third-party library. So I'm considering that. And similarly, let's say if I want to import the NumPy, so I just simply write import NumPy as NP. Okay. Now from Sklearn, import first. I don't have any data with me, so I will be using the Sklearn pre-built data. So Sklearn itself is providing you a lot of diminished version of the data. When I say diminished version, that means those data sets are quite huge when we load it from, let's say, any of the source where the data is available. But for the training purpose, whosoever is actually learning it for the first time, the Sklearn itself provides you few data sets. Why? Because so that you don't have to wait for hours of time to just get the training completed, just to understand what kind of accuracy you are achieving. So what they have done is they have a few data sets with a diminished version, shorter version of it, lesser samples, lesser attributes, so that your result will come within fraction of seconds. So at least you can have an understanding. Then later on, what we can do is we can actually start building on the larger data sets. Okay, so for the larger data sets to improvise on the accuracy, we can move towards the deep learning also. That's on the later stage. But here we are just trying to understand what it is. Let's have the essence of a smaller data. So we have a sub section that is data sets, I suppose. Let me check. Yeah. So data set is first. I'm importing separate subsections because Scikit-learn itself is a very huge library. So it's having a subclasses inside it. So it's always advisable, don't import everything from the Scikit-learn because it's a very huge library. So automatically it makes your whole environment of the Python very huge because it will load everything on the RAM. So that is never advisable. Whatever section, the function of those section you are supposed to use, it's always a better option to just give the name to it. For example, from Scikit-learn, I'm importing the data sets so that this particular section is only having the few data sets, diminished version of it. And then I would like to load, let's say, matrix. Matrix is what? Matrix is for the evaluating parameter that you have seen yesterday: precision, recall, accuracies, F1 score, confusion matrix, all of it. So you'll be able to see that. Then if I show you the next one, I need the classification model. So for today, I will be using this term only, classification model, and I will be using one of them. In the next session, we will go a little bit technical in terms of how it is reaching to the solution. But for the coding, just consider this. I will not be changing anything. I will not change any hyperparameter. I just want to give you a sense of how to build it. So that's your SVM, support vector machine. I'm just considering the function of it. Okay, now one more section I want. The section which will help me out in dividing the data or splitting up the data, more better term, splitting up the data into training and testing. For that we have model underscore selection. So now from the Scikit-learn, I'm using these subsections. Okay, next, import numpy is already there, Scikit-learn is already there. No, I don't need anything else. Now, so how to fetch the information? For example, I would like to load the data. Until you have the data, you can't do anything, right? So load the MNIST data. I'll show you what it is. For that, like I have to load it. Let's say data sets. Now this data sets is available. So I will be using this term data sets, then dot. Then whatever data set that you have, you can just press the tab. It will show you all the possible data sets that your Scikit-learn is already having. See this. Whatever you see with the load, they are the diminished version. We have full version also. Fetch OpenML, fetch face data. Fetch means it will directly load it from the server, which we don't want right now. So let me load this, load digits. Digit dataset is one of the benchmark dataset. Let me show you. If we are working on the machine learning model, then we have to go through with this MNIST handwritten digit dataset. So can you see over the top over here? This is the digits. Actually, it's like total. If I talk about total, so it's like more than 60,000 digits we have for the training and 10,000 for the testing, right? This is, can you see that it was introduced in 1990 and it's a benchmark data set for classification. So whosoever is working on classification or recognition, they have to post their results at least on this handwritten digit data sets, because this is to recognize the handwritten digits on the basis of the training that you perform. Okay, so see this. It's like having a combination of zeros, ones, two, three, four, five, nine. Let me click on this. Please, just I want to show you one specific thing. Total images, it's already mentioned in this sentence, is for the training purpose, 60,000, for testing purpose, 10,000. That means you're not supposed to modify it. It's already there. It's already there. They have done this modification for you, 60,000 for training and do the testing on 10,000 images. So 60,000 have different combination of zeros, 1 till 9, and then 10,000 also have zero combination of 9. So in the testing data, we do the testing and then try to compare it with the present data set. That is one thing. But more importantly, each image is a size of 28 by 28. Okay, so this is real data. When I say real data, that means that is a complete benchmark data of 70,000 samples. So this is MNIST database. Now I will show you the Scikit-learn version of the MNIST. Then you will see what is the meaning of diminished version. Let's see over here. When I do this, what I'm doing, I'm just trying to load the digit data. Once it is loaded, let's write print type data. What type of data it is? It's a util bunch, means it's a Scikit-learn bunch which is having a lot of information in it. Now, how to fetch that information? With a dot operator. Data dot DESCR, I suppose, description. So we have a full description also here. Can you see this is optical recognition of handwritten digit data sets? Total number of instances, see how many? 1797 only. So it's having a total data set that is only 1797. Number of attributes is only 64. That is, each image is of 8 by 8. What they have done is, they have created the features out of the image by just doing nothing, by just doing the reshaping. 8 by 8 is the image size. You remember what is the size of the actual data? 28 by 20. So here it is all in a pixelate form because they have reduced the size of the image also. And the number of attributes that you have is 64. 64 is right. You just flatten this. When I say flatten, that means convert everything in a single dimension. So 8 into 8 is 64. So number of pixels are actually those with the help like the image, and that image is converted into single dimension and created as a attribute. So if you compare it with the credit card data yesterday, the columns that you were having, now there were only 4 columns. Here it is 64. That's the difference. Okay. Now let's see how we can use it. So we have loaded our data. Now what we have to do, we have to extract the data from this util bunch. So to, let's say, extract the data from this util bunch. How would I do it? Let's say, if I would like to know where my data is, so data in this, if I press the tab, then you can see these are the few things available. Okay. So now let's say for an instance, so I will show you this teacher names. Teacher name is not required. Teacher name, target names. If I print it, these are the possible target names. Target name as in, this is the digit data set. So possible targets are 0 to 9 only. 0, 1, so few will be 0, few will be 1, few will be 2. So this is one thing. Print target names. Now if I write print data dot targets. Let's don't print the name, just print the target. So these are the targets. How many it is? I don't know. Dot shape 1797. Where is my data? Data dot shape. That's your data which I was talking about here. The attribute, 64 attributes. So we have 64 attributes here like this. Now, if I talk about the image, so this gives you the image also, images. These are all the images, and let me show you the shape. You will see the shape, little bit difficult for you. So each sample is having 8 by 8. So it becomes a 3D stack of 2D images like we have in the books. So each page representing each image, and it's a stack of those pages. So 8 by 8, which is converted into a feature like this. Why they have converted into a feature? Because the machine learning algorithms, they cannot be processed with a 2D data. That's why the requirement was to convert that 2D data into single dimension. That's why this 8 by 8 is converted into 64. So this is, they have already prepared for it. You don't have to worry about it. Okay. But sometimes, like when you are dealing with the actual data set, like we will be building the face recognition model. So when we build that model, what happens is you don't have this automated stuff because you are loading the face data sets or any image data set from the hard disk. And then you have to do that conversion. You have to convert the 2D images into single dimension that will be represented as a feature, and then you can process it in your machine learning model. So always machine learning models seek for a single dimension data, and how it should be, all your attributes should be in the columns and your samples should be in a row. If it is like this, then only you will be able to call that function. Otherwise, no. It will keep on giving you error again and again. Okay. Now, so this is just the analysis what the data is. Now let me separate it out. I'm just shifting my data into X variable. So this will have data attributes. And in Y, I'm shifting my targets. Okay. So this will have respective labels. Can you see this? 1797, this is also 1797. So each and every sample, this attributes having the respective labels over there. So I shifted it in the Y. After this, let's say I'm shifting the images also in image. In this case, we have the images, otherwise generally we don't have it. So this will have all the respective images. Now, my first task is to visualize. Actually, if this is an image, so we could have seen it. So let's see it. Okay, so how we can see? Let's say, for example, now I just executed this. This is what shifting the data and images in a separate variables. Okay, so this is what I did over here. This is just analysis of your data where we have what, and that's your shifting of the data. Please, that's section by section. That's the set shell number 2, and this is the shell number 3. Now, my requirement is to visualize the data. So for the visualization, we need that this import matplotlib dot pyplot as PLT. Okay, just to visualize. Now, how I can visualize? Let's say I'm taking randomly any sample from this image. Let's say current image. Please, everyone. np dot random dot. Okay, random. You will get more confused. But let me just do it like that. It's an image. You saw this. As per this, what I should do, I'm taking, let's say, 101 sample, all the values of the second dimension, that is 8, and all the values of the third dimension, that is this. So I'm just extracting 101 number image. I would like to display this. PLT dot figure 1, PLT dot IM show, IM, and then here the CMAP should be gray because it's not a color image. Then PLT dot axis off. If I run this, can you see? It's a pixelate because it's only 8 by 8 pixels, but we can see, yes, I think it is O. But how would I verify that it's O? I have to fetch O as in, sorry, 0. How would I verify? From the Y, let's exactly this same position value, let's print it on the title. PLT dot title round bracket Y square bracket 101. So the sample number exactly the same. So it will print that specific. You see this symbol. So to automate little bit this thing, let's say SAMP equals to this time 1000. So instead of 101, just write SAMP. 101 here, just write SAMP. So you can see with this variable, it will change it automatically. This is 1. Oh my God. And let's say 10. This is 0. Do we have anything else? 13, 3. That's pretty pixelated 3, we can see. But this is 3. Where I can have 5, let me see. Yes, so this is 5. So now we have to recognize this. This is just for training purpose. Otherwise, you can see these clear pictures, whatever I show you this. Exactly this form we see whenever when we load. I will show you that also. When we fetch the complete data set, then you will exactly see these things. Okay, so that's like only showing one single image, please. But out of my curiosity, I really want to show my database exactly in this form that people are showing like this, which I like it. This, like having a 1, 2, 3, 4, 5. So 5 by 6, 5 by 5. This is 5 by 5. This is 4 by 4, right? So how I can have any random sample printed and how I can present it like this. Now my target is to have, let's say, 8 by 8. Not 8 by 8, let's say 7 by 7. Let's say have multiple 7 by 7. That means total 49 images. Let's say how we can do that. So if you have an essence of subplotting, or if you don't have it, like generally what we do, I'll tell you, we first open up the one single figure, that PLT dot figure, and then we divide this figure into multiple subfigures like this. So it works in a concept of row and column. For example, if we want 7 by 7, so it will be like this. For example, this is the number of columns, and this will become number of rows. And if we write 7 by 7, so this also will be 7, and this also would be 7. So it's 7 by 7, and the indexing starts with this is 1, then this is 2, and then this is 3, and so on. Okay, so this is how we divide our single figure into multiple subfigures, and each figure can act as a separate figure, or rather separate section where you can paste any image. Okay, so that's what we know as subplotting. Okay, so subplotting always see it's have a syntax plt.subplot like that, plt.subplot round bracket. Now the number of rows, comma, number of columns, and which index you're talking about. And just after that, we write plt.plot. Then in this particular command, whatever plot you want to show will be plotted on this index. Then you have to keep on changing. Okay, so we will not write it 49 times. You see the same repetition is going to happen over there. So we'll be trying to use the for loop. Okay, so let's see how we can build this. Now let's say, for example, here, for I in range, I need how many? I want to start from 1 index. I have to check the index and I have to go exactly till 49. It should be 50, comma 1. Okay, and then plt dot figure 1. See this. This was for the single image. Let me copy this. All are for single image. Why to write again? And this sample should be randomly changing. Then that's what I was using this np dot random dot rand int round bracket. This is to generate any integer number in between certain range. So my range here is starting from 0 to 1796. Okay, and which how many numbers I want to generate? 1. But this always gives you the result in array list. So you have to address the first element of it. Now this is okay. That's it. But this plt.figure will not come over here. It should become over the top, and here it should be subplot. And then index. How many total number of rows you have? 7. How many total number of columns you have? 7. Which index you want to print currently? I. So with respect to this I, index will change. Index will change using I, and sample will change using samp variable. So that's why in every iteration, you will see a change in the image and change in the position. But if I run it now, you will see a very weird, see this, very small image here, because this is a standard size. How to deal with that standard size? We can increase the fixed size. That will be changed with respect to the resolution of the screen. Okay, so I just pass the ratio. For example, the row and the column ratio. Let's say 10 by 10. See, little bit more informative. 2, 2, 3, 3, 6, 6, 9, 9, 1, 1. This is pixelated. That's why, but still we can see here 8 is that's looking like 8. This is 5, very nice 5 here. This is 4. 8 by 8 pixel only. Still we are able to see which digit is what. So that's for your reference, please. And how I'm able to say that it's a subplot. Just right click. I'll show you. Right click, save the image. Try to have it in your system also. Save the image as, let's say, image demo. Okay, and then not in the Jupyter. Let's say have in the desktop. Save it. I'll show you. Yeah, this one. See this single image loaded. These are the type of images that you see on Google whenever you search for this. So this is how it is being built. It's not rocket science. It's pretty simple. Okay, so that all the 49 images are now in front of me in one single image. That is what the subplot is. So now we have a set of attributes with me. When I talk about 64, so this is 8 here, this is 8. Now, when we have this 8 and 8, I'll tell you how it is created. Now, how the image of 8 cross 8 is converted into a 1 cross 64 feature attribute, which you already have it over there in one variable, but how they created it. So for that instance, let's say I'm taking up this one single image. Let's say I'm just taking one single image here. Now this is image, print im.shape 8 by 8. Now let's convert this into a feature. So for that, let's say feed equals to im.reshape. Reshape, how you want to reshape it? If I write, see, I have to calculate 8 into 8 is how much? 64. Then I have to write 1 comma 64. If I do it, print feed.shape 1 comma 64. That is the feature. But I have a shortcut way also. Instead of writing 64, just write -1. -1 means all the elements in a NP array will be shifted to where you have written -1. It could be either column or row. In our case, it is column. Why? Because -1 is over there. If you write -1 comma 1, let me show you. -1 comma 1, then it will become 64 comma 1. But this is like having all the rows. All the samples are there in all the rows. I don't want it. I want it like that. That's why it becomes a feature attribute 1 cross 64. So this is how they converted and saved and created a stack of 1797 comma 8 comma 64. We are not supposed to do it, but at least we should have an understanding of it. So that's for you just to understand. Now I already have a feature. Let me write this again. That's X and Y. Only this X and Y. Okay. So data, features, and labels are this. My first step towards the machine learning model is split. You remember over the top I wrote, we have the data now. Now what the first task? The first task is to split the data into 2 parts. Split it into training and testing. Okay, so split the data into training and testing. That's my next part. How would I do it? I'm not going to do it manually. I have a straightforward function for me. Model underscore selection dot train test split. Okay, then what do we have to write over here? What is my data? What is my y? And what is my test underscore size? Here we have to specify TR is to test ratio. For an instance, I want 70 is to 30. I'm just taking that same benchmark which I used yesterday. So we wrote it like this. It says 0.7 colon 0.3. Okay, so that becomes training and this becomes testing. Training, testing, training, testing. So you only have to pass the test size. Training will be taken autonomously. So that's your 0.3 means 30% testing ratio. Now, to fix this means n number of time you rerun it, there is no problem. But whatever sample which is being taken as training in the first run and as testing in the first run should remain same, because inside this is a random shifting, random shuffling of the data. How to fix up the random shuffling of the data? These questions also get asked a lot of times. So we fix up the random shuffling of the data by fixing up the seed of the random data generation. So that if you fix up the seed, so whenever you rerun the code, it always remembers that, okay, you started the code generation from, let's say, any positive integer number, then you will get the same values, the same data again and again. So there will not be any change in the accuracies. So we have one property as well, random state, give any positive integer number just to fix up the random seed. So this is about the input attributes of this function. What we are passing the complete data, complete labels, respective labels in that same positions. Then that's your test size, which is 0.3, that is 30% I want to ship for the testing, and fixing up the random seed with any number. It's not mandatory that you should pick 3, it should be positive integer number. Okay, and then what will be the outcome? The outcome would be X train. These variable you can use any, but just to use a self-explanatory variable, it becomes so informative for us that first is your X train, next will be your X test, third will be your Y train, and fourth will be your Y test. This will be the output of your this function. Okay, so this becomes this huge function here. So this is my splitting of the data. Let's verify this. So print, what was my data shape? Data dot shape. Okay, now what's my shape of this? X train dot shape, comma, Y train dot shape, then print X test dot shape, Y test dot shape. And here, let's say Y dot, not Y, yeah, this is much better, not data, X dot shape and Y dot shape. You see this 70 to 30. So out of 1797, 1257 went for the training and 540 went for the testing. So it's like that. For an instance, I will show you the change. If I make it 50%, just to check. So can you see this? 898 went for the training and 899 went for the testing. So this is how we can simply just change. Okay. Now create the, I will use the name classification model. Classification model for training and testing. That's also not difficult here. We have straightforward function for everything, but the structure should be clear in our mind. So now let's say we are building SVM model. SVM dot SVC. Each classifier have two type of capabilities. One is they can be built as a, when I say classifier, that means I'm talking about the supervised learning algorithms. Okay. So when we talk about the classifiers, they have two type of capabilities. One, acting as a classifier, those algorithms, and second is acting as a regression. So we can create them as regressor as well as classifier. That's why we have two things here, SVC and SVR. So only two things. Either I can use it as a regressor to build the forecasting models or prediction models, or just classification model. So two options are there. So when we do the regression, then you will be able to see these. But right now we are working on the classification, just open to it. We have a lot of attribute which we pass here just to tune our hyperparameters. But as of now, we are just building a first single classification model. Let it be default. So default here is for me just a training model, okay, which has the capacity to get itself trained for any sort of data that we have. Now, how we can do that? Let's say now I've created a model. Now train the model. Train the model feeds. What I have to pass? Using train data and its respective label, that we don't have to forget. Whenever we are doing the training, we are passing both the things. We are passing the data as well as its respective labels. How? Let's see this things. SVM model equals to SVM model dot fit. Fit is for training. No matter which model you are building or which library you are using, you will be using TensorFlow also, you'll be using Keras also. In that also, whenever you see the fit, that means now the training starts. So this is used for the training. Just write, pass two things only, nothing else. Xtrain and ytrain. That's it. Once your training gets completed, then you have to predict or test the data, or rather test the trained model using test data only, no labels, only test data. Okay, so let's say, so it will give me the result. Let's say I will save the result in OP. So SVM model dot predict. So predict is for testing. What to predict? Y test. I'm only passing the test data, that is Y test here. So I will get the result in what? OP. So this is what, like yesterday, what we did, we splitted our data into two parts, train and test. We already did it here. The next stage is we pass the train data in the classifier. So we first created the classifier, then pass the data in the classifier for the training. Then we achieved or obtained the trained model. Now with the trained model, we are trying to predict the labels of the test data. Now, which is saved in the OP. First, let's analyze the size of OP and Y test just to check exactly both have the same size or not. OP.shape, Y test.shape. So you will see that yes, both have the same size because exactly each and every sample is getting, you can say, recognized, and that respective value is saved in their respective positions in the OP. That's why both have the same size. Now, evaluate the performance. When I say evaluate the performance, then what I have to calculate? I have to calculate the precision, recall, accuracy, confusion matrix, right? These things which comes in my mind, and F1 score. So we have to calculate this. Now to calculate these things, what we have loaded before? Metrics. So in metrics, we have all the supporting functions. We need to know what to call. If I know that part, so you don't have to derive anything. You have a straightforward function. That's more important. Let's say, let's see the accuracy first. So metrics dot accuracy score. The accuracy score will come only when you pass the Y test and the OP. Because these two you are supposed to compare, right? So we have these two things here. Then let's say confusion matrix. Confusion matrix, Y test, comma. You just write the initial of the function and press the tab. It will auto-complete. Confusion matrix. And then let's say, I don't want to evaluate these manually for all. I have a right away function which generates the complete report, class-wise report. Matrix dot classification underscore report, Y test, comma, OP. This will generate the complete report for me. Now, print accuracy of the system, comma, ACC. Print complete classification report. You can't write it like that here. Let's print report. Let's see these two things first. Accuracy of the system is 98.70. Complete classification should be class-wise. See this. We were having class 1. We obtained the 100% precision for it and 100% recall. F1 score is also 100%. What is this support? Support is how many number of samples considered for the class 0 in the testing data? 64. So out of 64, all are perfectly classified. That's why everything is 111. In the 1, we were having 56 samples. Out of the 56 samples, we obtained the precision 98%, recall 100%, F1 score 99%, and so on for all the classes. And this is the weighted average here. Okay, total is 540, and this is how the 540 obtained. So that's your complete class-wise report, and this is your accuracy of the system. Now let's evaluate the confusion matrix. Let's say print font. Can you see this confusion matrix here? Diagonal elements. All the diagonal elements are like this. Okay, and these are what? Few 111, which are misclassified. That's why this is misclassified. Now, can you see? Can you imagine like the previous yesterday's confusion matrix, or now this? It's only 10 classes data, but still this is the confusion matrix, right? So this is like actual, and that's your this thing. Now we can better visualize these confusion matrix using the heat maps. Let me show you that as well. For example, import C-bond as SNS. So C-bond is again for the visualization. I just want to use this plt.figure1. I would like to use only SNS.heatmap. Heatmap round bracket font. If I just simply do it, then you see the heat map something like this. Just simply write a note equals to true. Then it will show you the numbers also. Okay, and if you want to just increase the size little bit, sorry, this will give the error. This is fixed size. You have to be enclosed in a bracket. Fixed size equals to. See this. We can see clearly that these samples, and this is all your misclassification 111. One sample misclassified, rest all are perfectly classified here. That's what we wanted. Okay.